Well, so in this video we're going to look at an alternative method for solving systems of linear equations, which is going to be Cramer's rule. In that we're also going to learn how to find the determinant of a matrix. I'll show you what that means in a second. It's basically an operation that we can do to a matrix. And then once we do that operation, we can use those results to solve systems. This is my least favorite way to solve a system of linear equations. And it's really good for programming, and it's also really good for cross products. Even if you don't like it for solving systems, you'll still need this operation when you do work with vectors in later courses. So to find the determinant of a 2x2 matrix, and the matrix is just an array of numbers. We'll see how that's going to relate to our systems here in another couple minutes. For right now, it'll just be this array of numbers. And to find what's called the determinant, we go A times D, and then we subtract C times B. And that's finding the determinant. So for this one, and I just think of it as I start in the upper right corner and then I go corner minus the corners. So 3 times negative 1, and then it's always subtraction even if there's a negative number coming up. And this would be 2 times negative 5. You certainly don't need to show all that. I'm just doing it so that people can follow what I'm doing. And this would be negative 3 minus minus, I'm going to flip that to a plus 10, and then that would equal 7. And for this I should have been writing D equals for the determinant. So D equals 7. For a 3x3 determinant, that's a little more involved. So we're going to have a 3x3 system like this, and here's our values. What we do is we take, these are called cofactors when we think of them as going across. We're going to go A times what would be called its minor matrix. The way that we find that is what I have down here, where if you draw a vertical line and a horizontal line through A, its minor would be the stuff that isn't crossed out. So we're going to go A times the 2x2 system like we just did. And then we're going to work across to B, and same thing, we cross it out, and so its minor is these ones at the edges. And then that one is a minus, I'll get to that in half a second, and then we're going to go C, we're going straight across the top row is where we're expanding, and then draw lines through it, times its minor. I don't have to go across the top row. I can go across any of the rows and still follow this plan. You know, if E was going to be one, when I cross them out, my minor would be A, C, G, and I. So I can expand along any row, column, or diagonal that I liked. Normally, all things being equal, I would just go across the top row, do it the same way every time. There's this little minus on the B, and this is the sign array for the cofactors, and again the cofactors are these values that we're expanding along. It's not that they're positive, negative, positive. Think of this more as positive as leave the sign alone, and negative as opposite sign. As long as we are expanding along the top row, the only one you have to worry about is you're going to take the opposite of whatever's there in the middle. So let me show you what that would look like for this version. Most people like this next version better, believe it or not. Still looks bad, but either of these are helpful when you get to, like I said, doing cross products with vectors in a future class. So I'll do this version first with the cofactors and the minors. So if I'm going to expand along the top row, I would go 1 times, and then cross that out, and its minor would be right there. So it would be this corner down here. And then I'm going to go the opposite of the sign, so in that case it would be negative. If this had been a -2, I would have a plus right there. And so cross that out, and it's like a T, and I'd have the 3, 4, negative 6, and 3 left. And then we'd have +2, and then its minor would be these 4. So 3, 4, negative 1, and 3. And then we have to expand all of these and try not to make sign errors. So let's go, this would be 1, And then negative 1 times 3 would be negative 3 minus 3 times negative 6 would be negative 18. And we'll clean that up in a second. Minus 2, that's right there. And then 3 times 3 would be 9 minus negative 24. And then 2, 3 times 3 would be 9 minus another negative. And cleaning these up, negative 3, that would be plus 18, times 1 would be 15. And then we'll just do minus 2 there for a second and get this put together. So that would be 33. And then 2 times, that would be 13. And so then, sneak over here. So 15 minus 66 plus 26. And I should be writing d equals. I'm really bad about that. And so down here, d equals, that would be negative 25. So that is one way. The other way is to write down this matrix, and that's what this one right here is showing. And you duplicate the first and second columns again to make the fourth and fifth columns. And then what you do is you multiply down each of the diagonals. So all this mess over here is going, multiply those three together, that's your first number, multiply those three together, second number, those three together, third number. And for those ones you're adding, I prefer to do this as minus and then all of this stuff with pluses, so that I'm just subtracting it one time instead of having to catch all three of those signs. And then we do for this we're going up the diagonals that way. Let me show it, as it will make more sense with an example than with just looking at that chart. So this would be 1, 3, 4, 2, negative 1, 3, 2, negative 6, 3, and then I repeat this one, 1, 3, and 4. I repeat that one, 2, negative 1, and 3. And then, so for this first round, we're going to go down the first three diagonals, which is how many there are. So 1 times negative 1 times 3 would be negative 3. And then we're going to add to that 2 times negative 6 would be 12, times 4 would be 48, and it's negative because of that sign. And we're going to add to that 2 times 3 times 3, so 2 times 3 would be 6, times 3 would be 18. And then we're into the subtract portion. So for me, like I said, I like to put a minus sign out front, and then I'll just add these three numbers and then subtract them all at once. I think the signs are easier that way. So this starting at the 4 and going up would give me a negative 8. And then that would be negative 18. And then that one would be 3 times 3 would be 9, 18. So we'll combine a little bit, putting those together, we would get negative 33, and I'll get my D in there. And then we're subtracting, the 18s are canceling, so it would be subtracting just that minus 8, and negative 33 plus 8, same 25 that we got back there. So that is how you would find two different versions of solving a 3x3 for a determinant. This next thing is just a brief. There aren't these on the homework, but I just need to show this to make the homework questions make sense. We can write what's called an augmented matrix given a system of linear equations. So let me show you what that would look like. Instead of writing down all the letters, we just use the coefficients of the letters. So for this first equation, we'd have 4. That coefficient is a minus 1. It's a minus like that. 3. And then for that equals, and this is the augmented part of the matrix, it's augmented with the equal sign. We use a line to denote the equals, and then negative 67. So for this one I have a minus 2 in terms of the x. I'm missing a y term, so I would put a 0 there. Z would be 1. 33 is over here. And here I'm missing the x term, so we'll do a 0, negative 1 on that y, and then 5 and 43. And you can see this looks an awful lot like where we just were. And that's going to go into how we're solving using Cramer's rule, which is this next bit, which says if I have two equations similar to this down here, I can find 3 determinants and then use that to solve Cramer's rule, or solve the system. So there's a d, a dx, and a dy. And I think it's probably easier, rather than trying with all these little subscripts it's really hard to look at, let me just show you down here what each of those is going to be, and I think it will make more sense. D is going to be, and let me write this as an augmented matrix just to have done that. So there's our system. This side right here, this is D. So where we're seeing these D's up here, that's where we kind of lop off the equal side and we just find D with this. So let's do that much. So we're going to go 3 times negative 5, and then minus 5 times negative 2, which would be a negative 10. And so if negative 15 plus 10 would be negative 5. So that equals D. And then next I'm going to find dx. And when I have dx, I can go dx divided by d, and that equals that x. So this is just showing you're going to find the determinant of this stuff. What we do for dx and dy is when we're finding dx, the equal side replaces x. So that's going to look like 2 and 10, and then the same negative 2, negative 5. So 2 times negative 5 would be negative 10, minus 10 times negative 2 would be a negative 20. Negative 10 plus negative 20, or sorry, negative 10 minus negative would be plus 20. And so that would be a 10, and that's my dx. And then for dy, the equal side just replaces the y's. And we get z in a second. Oops, I said z out loud, so I wrote a z. When we get z, it's going to replace z as well. So this would look like 3 and 5, and then 2 and 10 right there. So 3 times 10 would equal 30, minus 5 times 2 would equal 10. So that would be 20, and that's our dy. And then what Cramer's rule does is says once you find those 3 values, you can take the ratio and solve for x and y. So x is going to be dx over d, and y is going to be dy over d. So here our x would be dx over d, which is 10 over negative 5, or negative 2. And then y is going to be dy over d, which would be 20 over negative 5, or negative 4. So our solution set after all that is negative 2 and negative 4. Next we have Cramer's rule, but for 3 equations and 3 unknowns. So what that means is we have to calculate these ones that we did back here. This bit we have to do that 4 times. 1 for d, 1 for dx, 1 for dy, and dz. And it's the exact same rule. Dx over d still gives you x, and so forth. It's just now we have to do 3 by 3 matrices instead of 2 by 2. I'll start this example for showing it for x. I'm not going to do dy and dz because it's the exact same thing, and if you can get x, you'd find 2 more matrices and you would find y and z. And so let's go ahead and write out d. And I'm going to do this by, I'm actually going to do this by the second method. So I'm going to do -1, which I actually should have that bar there. Sorry, 1, -1, 2, and then this would be -1, 1, and -1. So -1, 1, and -1, and then 1, 1, and 2. And then I just copy these rows over. And then always a good idea, especially when there's like a lot of ones running around, I'm going to double check my notes and make sure I have all of those signs in the right places before I go further. So 1, -1, 1, 1, negative, -1, 1, 2, 2, 2, -1. Okay, that one looks good. Always good to double check that. And so then I'm going to multiply down these rows, right? And that's going to give us our first 3 that we add, and we'll multiply up the diagonals the other direction, and that's going to be the ones that we end up subtracting. And for this, we're solving for D. So 1 times 1 times 2 would be 2 plus -1, 1, and 2, so that would be a -2. And then 1, -1, -1, so 2 negatives would make that positive, so +1. And then we'll subtract 2 times 1 times 1 would be 2. And then -1 times some more 1s would be a -1. And double negatives, that'd be positive, times 2 would be +2. So this would go 2 minus 2, so that's 1. And then 2 plus 2 would be 4 minus 1 would be 3. And so it looks like D equals 1 minus 3, so -2. And then I'm going to do the same thing, but I'm going to find dx. And so in this case, the 1, -9, -4 would replace that first column there. And then copy down the next 2 columns. And then repeat these 2. So -1, -9, -4, and -1, 1, -1. And same thing, I'm going to pause here for a second and just make sure I don't have any miscopies. Nope, that all looks good. And then this is going to give us dx. So kind of multiplying down, I would get -2, and then that would be plus 1 times 1 times 4 would be 4, double negative, and then 1 times 9 times 1 would be 9, and then subtracting -4, and then that would be a +1 because of the double negative, and then double negative again, so plus 18. And let's see, so this is going to be 13 minus 2, so that's 11, and then minus, that'd be 19 minus 4, so that should be 15. And so that equals -4, so dx equals -4. So then to find x, I would do -4 divided by -2, and x would be 2. And that's where, if you wanted to find y and z, which I don't because, again, it's the exact same process, you would just go ahead and do the same thing for y and same thing for dz, and then do your ratios, and that would solve out the system.